Students, we have few more things to do, and one is called. We'll see what it is. Okay, I don't want to say the name. I don't use. Sometimes I don't like saying the name before we learn the stuff. Okay. Anyways, you studied the differential of x. Differential of x. You studied that. I mean, I showed you. So differential of x, or I could also write it as d of x of 1. I mean, d of x to the power 1. X to the power 1 is same as x. So differential of x to the power 1 is, okay, yeah, we'll do that later. Then differential of x square you learned, differential of x cube you learned, differential of k to the power 4. This some of this were homeworks, some of this I did and showed you in a previous video. So you guys saw all this. Now let us start doing the answers. D of x to the power 1, or differential of x, is 1. D by dx of x square, 2x. D by dx of, or I could write 2x, I could write it as 2x to the power 1. Same thing. You will see why I write like that. Okay. D by dx of x cube is 3x square. D by dk of k cube is 4k cube. Fine. Now suppose I'm changing the variable. Instead of k, I want to change some other variable. I'm putting x, dx to the power 4 by dx. So the answer will be 4x cube. Now if you look at all these things carefully, you will notice a pattern. This 2 comes here, this 3 comes here, this 4 comes here, and then minus 1 happens here. X to the power n, n could be any real number. Okay, n could be any integer, any rational number, no problem. It could be any real number. Okay, now x to the power n, if I differentiate it, so d by dx of x to the power n is, and by the way, you should make sure that the variable which I am differentiating with respect to the variable which is in the function. Only in that case this is valid. Okay, this is true. So d by dx of x to the power n is nx to the power n minus 1. That is n into x to the power n minus 1. You can see in all these cases it is true. So see, 1 is equal to 1x into 1x to the power 1 minus 1, which is 1 into x to the power 0, which is 1. 2x to the power 1 is 2x to the power 2 minus 1. 3x square is 3x to the power 3 minus 1. 4x cube is 4x to the power 4 minus 1. So you see, this is a general rule. I mean, it applies for all the numbers, all the variables, provided n is a real number. If n is not a real number, if it is an imaginary number, this need not be valid. Okay, so this condition is valid for n is a real number. Do remember that. Now, and also remember d of x to the power n, d by dx of x to the power n, we are differentiating with respect to the same variable which is in the function. Okay, now this rule, or this equation, is known as power rule, because it has powers, so that is why I think so, that is why they call it power rule. Anyways, now this is one thing which you guys, so from now on, you don't have to do that f of x plus dx minus f of x divided by dx, all that you don't have to do. Why? Because you have this thing, you can directly use this formula. Now I would like to show you a visual proof on how differential of x square is exactly 2x. Please give me your undivided attention to understand this. Let me take a square with sides x. So the length of the side of a square is x, and therefore the area of a square is x square. Okay, now what do we mean by differentiation? we are adding a small value, a very small value, right, to the input. So we are adding a very small value to the input, and then we are seeing what change it brings in the output. That is what we are doing, right? So the input here is the side, the length of the side, which is basically x. The output is the area of the square, that is x square. Okay, we are adding a little part to the side. Okay, a little to the input we are adding. Now let us look at what we just added. We added the length of the side is x. With the x we added a small dx. Okay, dx. Now here also the same thing, we added a small dx. Okay, now guys, tell me what will be the area of this rectangles. Okay, before that, look at this. There's a tiny square here. See, two rectangles, and then when we extended, we got a square also here. So looking at this square, what is the side? Dx and dx, because we added dx's, so the side is a dx, added dx. And what will be the area of this square? The area of this square will be dx into dx, dx square. What about this rectangle, this small rectangle? It will be length into breadth, x dx. What about this rectangle, this vertical small rectangle? X into dx, length into breadth, x dx. Perfect. So this is our final thing. Now we have two areas, old area, new area. Our old area is x square. We started with x square, no doubt. What is our new area? Our new area is x square, our previous square, plus x dx, that is one of the rectangles, the down rectangle. Then this x dx, that is this rectangle, plus dx square, that is dx the whole square, dx whole square, that is this green square. Now x dx and x ds are like terms, so I can bring them together. So it will be x square plus 2x dx plus dx square. Now look at this dx. Dx is a very small value. As you all know, it's a value that is approaching to 0. Not equal to 0, but it's approaching to 0. Now let's take any very small number for an example. For example, 0.000000001. Square the value. What will you get? 0.000000001. So if you square a very small number, that is, if you square a number below 0, not below 0, I'm sorry, a decimal number, you will get an extended the decimal values will be a little more extended. Basically you see that 0.001, such small numbers, when you square it, you get very teeny mini numbers, very small numbers, and therefore this dx whole square can be neglected. We can take it off, because it doesn't matter much. It's a very tiny, the dx is a small number, and that is important for us. Now dx square is too small. We don't even have to count it. You get it? See, 1 plus 0.000000001 doesn't make much difference. It's almost equal to 1 itself. Same logic. Now what's the change in area? Change in area is new area minus old area, that is 2x dx. X square plus 2x dx minus x square, you get 2x dx. So what is this thing? This thing is equal to change in area. We started with differential of x square, right? This happened, this is the change in output of x square. X square is our output function, right? Now bringing into the differential form, that is taking this dx, I forgot the equal sign, then taking this dx and bringing it down, I get this beautiful thing, that is differential of x square is equal to our differential of x square with respect to x is equal to 2x. d by dx of x square is equal to 2x. Do you see how it all came together? Okay, so the same applies for x cube also, but for x cube it will be a three-dimensional figure. It will be basically a cube itself, and we will not be finding the area. Area is always a two-dimensional value. We'll be finding the volume, length into breadth into height. So volume is x cube. Volume of a cube, you all know, you have already studied, it is x cube. So I am not going to explain this, I'm just going to give an idea. And it is like, you have three squares, three different squares. Now each square's area is x square because the length and breadth is x. So this is how it works. Okay, now so differential of d by dx of x cube is 3x square. I'm not explaining to you how it is coming, but I'm just giving you an idea. I think you get an idea of how it comes. Okay, so that is all about our power rule. Okay, so next video we will see about just few more rules. Few more rules are there that we'll see in the next video.